When we meet on Sunday, we're going to be in the library. The reason why is the librarian has agreed to give a refresher training on how to find good, reliable sources for your research project. And so on the ground floor of the library is a computer lab. It's room IC2. So you go in the library. As you enter the ground floor, it's on the right side. They said that they'd have signs up that day. But please be on time because we're going to begin right at noon there in the library. And I'm going to go into detail about the research paper. The one thing that you maybe want to start thinking about before then, I'd encourage you to read the whole assignment. But everyone's going to have a topic. Everyone's going to have a different topic. And so if you really want to have your topic be DDT, for example, then you need to sign up for that before someone else takes it. I have a sign-up sheet, and so you can sign up after class, or you can sign up before class, or come to my office and sign up, but it's an individual project, and everyone has a different topic. All right. Homework 7, I've handed out an update to homework 7, excuse me. I've removed a couple of the assignment problems, and I've clarified one as well. So the old paper I gave you for homework 7, you can throw that away. This is the new one. The new one is posted on iLearn. If you want to make sure that you're doing the right one, just look online. So that one's due on Tuesday the 27th, and then I'm going to keep putting announcements for the research paper. The first draft that you have to write for part 1, which is only 2.5 pages, 1.5 spacing, that's due on Thursday the 12th of November. So, that's not an immediate thing, but it'll be here before you know it. Any questions on these announcements? Yes, it's an individual project. No. No, it's an individual project. It's a research paper, and so each student is going to have to write, in total, 5 pages. Part 1 is 2.5 pages minimum. Part 2 is 2.5 pages minimum. And each student will have their own topic. Okay. Disinfection. So far we've talked about the rapid mix basin where we add the coagulant. We've talked about flocculation, where the colloid particles have collisions and grow. We've talked about sedimentation when the particles are settling downward. We talked about sand filtration when those few remaining particles that didn't settle have impaction and adhesion inside of the sand filter. And so the water that comes out is very clean. In a good water treatment process, the turbidity will be very, very low, and there will be hardly any viruses and bacteria. But what we prefer is 0 viruses and bacteria, not hardly any. Hardly any is pretty good, but even better is no bacteria and viruses. So disinfection is the final step. Chlorine is probably the most common disinfectant, but there are some others we'll talk about as well. So we've had all these other steps, but what still sometimes remain are the things that actually cause the physical ailments in humans. Cholera, typhoid, amoebic dysentery, these are all diseases that are waterborne, and when water is untreated, it causes a lot of deaths worldwide. You can see that, for example, in the year 2000, there were 17 million people that had typhoid. When there are outbreaks of cholera, it's a very, very virulent and dangerous disease. It has a death rate of between 50 to 90% fatalities when someone gets cholera. Worldwide, there are more than 2 million deaths due to amoebic dysentery. And so there's a lot of trouble that comes from untreated drinking water. And so that final step to make sure that these concerns don't happen is disinfection. Here's some more statistics just to give you an idea of the scope. They say that of all the people who have diseases in the world, 80% of the people that are sick right now got sick because of a lack of clean water. Whether it's sanitation for washing their hands or they drank unclean water, but 80% of the people, and usually we think people who have a disease or are sick, it's maybe because they have cancer or maybe tuberculosis, and those are really big important diseases, but just in terms of the numbers and the damage it does worldwide, unclean drinking water is by far the biggest problem that the world has with disease. half the people who were hospitalized got there because of sanitation-related reasons. So disinfection is a way of killing the pathogens that are in the water. You know, the cholera, typhoid, all of the things that would make us sick, we have to inactivate or destroy that while it's in the water. And chemical disinfectants like chlorine are the most common. And here's a list of some of the chemicals that are used. If you ever go camping, maybe you've been camping before where you used iodine to purify drinking water. It's a portable way. Ozone is a chemical disinfectant that's formed when you can actually form it with electricity. Yes?
Just like put chlorine in water.
Yeah. Chlorine, we'll talk about how chlorine is formed. Bleach is an example of chlorine. And if you're ever in a situation where the drinking water is contaminated, you can put a few drops of bleach in the water and it kills the microorganisms. Yeah. And it doesn't have a great taste. Chlorinated water actually doesn't taste as good as unchlorinated water, but it's better to have the bad flavor and not get sick in some cases than to be sorry later. So one category is chemical disinfectants, and we'll talk about those. The other main division of disinfectants are those that are able to kill the pathogens in a physical way. So if you heat up the water and boil it, that's not chemistry, that's heat. And so you're killing it physically. Or if you use a membrane to strain out the bacteria, like with a filter, a membrane filter, that's a physical barrier. And UV radiation, like shining a bright UV light, can also kill pathogens as well. I put a smiley face there because sometimes we can avoid problems when we use physical disinfection. You know, the flavor of the water is better. But then there's also something called disinfection byproducts. On the homework, the last two questions here, question 4 and 5, you're going to have to do a little bit of reading in the book or maybe a Google search to answer that. It's a short answer question, but I'm not going to go into a lot of detail. I'll tell you that disinfection byproducts are formed when chemical disinfectants combine with organic matter and water, and they can be carcinogens. They can cause cancer, the byproducts of disinfection. They're in very small concentrations, and so it's not a huge problem, but when you do just a little bit of extra research for problems 4 and 5, you'll find that out. One of the ways that we quantify disinfection is with a logarithmic scale, because disinfection is so effective that there isn't very much left after we disinfect. There isn't very many viruses left. So there's this phrase, 4 nines of removal. That would mean it's 99.99% removal. So the 4 nines, 1, 2, 3, 4, that's what it's talking about. So 4 nines of removal means that if you had 10,000 bacteria, then 9,999 are killed and only 1 remains. And so this is the formula we use to express the removal of pathogens through inactivation. It's the ratio of the inflow to the outflow concentration. And so in this example where we were saying there's 1 who survives out of 10,000, 4 logs of removal is just that if you have the log of 10,000 divided by 1, the answer to that is 4. Percent removal, you can see, is it can be calculated as a function of log removal as well. Does everybody have a copy of today's in-class exercise? Okay, this is a quick one. I'd like you to get started on this. We know that there's 50 milliliters of water, and here's the number of typhoid bacteria. So what's the concentration of bacteria after disinfection for this one? So finding the influent concentration is the number of bacteria divided by the volume. You can find it's 1.12 times 10 to the minus 10 to the 5th typhoids per milliliter. So that's a lot. Every milliliter of water has that many bacteria in it. But after disinfection, if there's 3.5 logs of removal, then after disinfection, then there's only 35.4 typhoids per milliliter. So if we express that in terms of a percentage, that percent removal is 99.968. So it's more than 3 logs of removal, because 3 logs of removal would only be 99.9. So it's 3.5 logs of removal. So this 6.8 at the end is that extra amount of removal that comes from the 0.5 in 3.5 logs of removal. Okay. It turns out that on average, the average person needs 10,000 typhoid before they get sick. It varies from person to person depending on your immunity and the strength of, the strength of your immune system. But how much water would you have to drink to get sick if it takes 10,000 to become infected? If you wanted to find out how much to make you sick, it would be 10,000 bacteria to get sick, and we said that the typhoids per milliliter is 35.4 typhoid per milliliter. So how much water is that? It's about 30 milliliters approximately. Anybody with a calculator do that calculation real quick? How much? 282.5 milliliters. All right. How much is a bottle of water? 500, right? The average bottle of water is 500 milliliters. So if you drank a bottle of water that had only had 3.5 logs, then it would make you sick. So we have to do better than 3.5 logs if this is how much typhoid is in the water to begin with. Hopefully we're not drinking water. Hopefully our water source has less typhoid than that. We're in trouble if it doesn't. Let's talk a little bit about what makes a good disinfectant. There's some criteria. A good disinfectant is one that actually will kill the pathogens, and it does quickly. You can see a reasonable amount of time and in a good temperature range. The reason why boiling water isn't a good disinfection method is it takes a lot of energy to boil water. It's very energy, and it also takes time to heat it up. And so that's one of the reasons why boiling isn't a preferred optimal disinfectant. Another thing that we have to say about the perfect disinfectant is one that does well regardless of the season. Water changes its temperature seasonally. It also changes how much maybe mineral content there is over seasons as we blend groundwater and surface water together. And so all those fluctuations, our disinfectant should be able to work with whatever range of water we're throwing at it. The ideal disinfectant is one that isn't toxic to humans, and it doesn't have a bad flavor as well. It should be reasonably priced, safe, easy to store, easy to transport, easy to apply and measure. Concentration should be easy to determine, and it should stay in the water after we treat so it can provide residual protection. The unfortunate thing is there's no such thing as a disinfectant that meets all of these criteria. Disinfection is always a balancing act, and it's always a compromise of deciding which of those do you want to keep and which one are you not going to keep. Here's a picture of the rail car and these big 1-ton cylinders that gaseous chlorine is delivered in. It's not safe at all. Chlorine gas was used in World War I as a chemical warfare agent, and if a big chlorine cylinder breaks open, it's very poisonous, and people can be harmed from that. So operators at wastewater and drinking water treatment plants often have to go through hazardous materials training to be able to be safe and know what to do if one of those cylinders breaks open. Mustard gas is different, yeah, but it has the same effect. It burns the lungs, it burns the eyes, it causes skin damage and blisters, and so chlorine gas is dangerous. Instead of using chlorine gas, it's a lot safer to use liquid chlorine, which is bleach, and that's what some drinking water plants have switched to just for preferred safety is hypochlorous acid, which is bleach. The kinetics of disinfection is that the rate of reaction is dependent on the concentration of bacteria that are present. In other words, if there's lots of bacteria, then you're killing bacteria very quickly because there's lots of bacteria. But once the number of bacteria is decreasing, so does the rate of reaction. What does that sound like to you? Zero order? First order? It's first order because the rate of reaction depends on how many are present. There's something called the CT approach. In the side of your notes, you don't have much room today because there's so many slides, but C stands for concentration, T stands for time. And to some extent, concentration and time are interchangeable, and so that if you have a concentration of chlorine in water, maybe a typical concentration for chlorine in water to kill the microorganisms would be 1 milligram per liter. And a typical exposure time would be 20 minutes. Okay, so C times T for this would be 20 minutes times milligrams divided by liters. The CT theory tells us, what if we wanted to have a smaller tank? You know, we don't want to have a huge tank that's big enough to hold the water for 20 minutes. What if we want to have a tank that's half that size and it's only large enough to hold the water for 10 minutes? The CT approach tells us that we still want to have 20 minute times milligrams per liter, and so what concentration should we use in order to make that happen? Yeah, if we use 2 milligrams per liter, you're doubling the strength of the disinfectant. You have to use half as much time to get the same net effect. You know, that's roughly true. There are some exceptions to that, especially at the extreme range. You know, if you used 0.01 milligrams of chlorine per liter, then that's probably too weak to have much damage to the cells of the bacteria. But within a reasonable range, the CT approach says that concentration and time can be exchanged for each other. Here's a tip for the homework. This slide isn't in your notes. I just added this in after I made the prints because I wanted to give you a little bit of extra help. So in previous notes this semester, I gave you the equations for a plug flow reactor. In disinfection, it's very common to use a plug flow reactor when you're applying chlorine. So in your homework, the graph that I've given you defines the K value. You know, there's the slope of the equation for a first order reaction. That's the K. And so you're going to put the K into this equation for first order kinetics in a plug flow reactor. And so just a reminder to put the first order equation into a plug flow reactor, and the K comes from the graph. All right. So how strong are bacteria? Some bacteria are stronger than others. Some are easy to kill, and some are very, very tough. It's hard to kill some of these bacteria. Giardia is a bacteria. It's actually not a bacteria. It's a spore-forming protozoan. And it's pretty hard to kill compared to viruses and bacteria. But compare it to Cryptosporidium. Which one do you think is tougher to kill, Giardia or Crypto? The way that we can tell is by looking for the same disinfectant, what dose is needed for a certain temperature. So this figure tells us if the temperature of the water is 5 degrees Celsius, in order to inactivate 3 logs, so what percent removal is 3 logs? Okay, so if you want to kill 99.9% of Giardia, then you should have 26 milligram per liter times minutes. So that means you'd have 1 milligram per liter for 26 minutes, and then that would kill 99.9% of Giardia. We need 858 milligrams per liter times minutes of chlorine dioxide for Crypto. And so you need a much higher dose So that tells us that crypto is stronger, especially because that's how much is required just to get 2 logs of removal instead of 3. So cryptosporidium is a very strong pathogen, and it's not very sensitive when it comes to chemical exposure. When we add chlorine to water, sometimes we also add ammonia. And adding ammonia and chlorine to water forms something called a chloramine. And a chloramine has a much better persistence in drinking water, and it will stay in the water for a long time, and so it provides protection as the water is traveling through the pipes. In case the water gets contaminated again, the chloramines will stay for a long time. They're stable regardless of the temperature changes and the length of time. And it requires a little bit more chemicals to add both chlorine and ammonia, but it gives you a better residual, which is why it's sometimes added. Some of the ways to get chlorine into water is with chlorine gas, and it's used because it's very inexpensive compared to liquid chlorine. Using bleach or sodium hypochlorite, it's a little bit more costly, but it has the benefit of safety. If the container of bleach breaks open and that bleach spills all over, it's probably going to ruin someone's pants. It's going to cause a mess, but it's not going to cause fatalities in the same way that chlorine gas does. Any questions about chlorination? UV is another way of handling disinfection, and UV is a way of not necessarily killing the pathogen, but what it does is called inactivation. The UV light shines onto the DNA in bacteria, and it scrambles the DNA. It actually, as the light is shining outward from a lamp, the water's flowing through this reactor, as it's called. The light is shining into the water. Any pathogens that are in the water have their DNA scrambled. In the same way that you can get skin cancer if you're outside in the sun for too long, people will get like melanoma because the DNA gets, these adjacent thymines get fused together. It's called a dimer. So the bacteria can't replicate. So if you're using ultraviolet disinfection, actually the viruses and bacteria aren't dead when they come out of the reactor, but they're not able to reproduce, and so they can't cause us any harm if they're not reproducing. And so UV is often used as a secondary disinfectant, along with chlorine. Some places will have chlorine and UV together because UV is very good at killing crypto and giardia. And giardia and crypto are kind of resistant to chemical disinfection, but they're a lot more sensitive to physical disinfection like UV irradiation. So that's the advantage of UV. And here, this figure just gives you an idea of some of the typical doses that are used when it comes to killing crypto, giardia, viruses. And the units of dose for UV are in terms of millijoules per square centimeter. The cost with UV is electrical cost. You're not having to purchase big rail cars full of chlorine gas, but there's quite a lot of electricity that's used in UV, and it's becoming a lot more popular. There's UV being used here in Sharjah at the wastewater treatment plants to avoid having to use so much chlorine. So it's getting a lot more common to have UV disinfection. All right. Before we break, let's just take one final look at these announcements. All right. Where are we going to meet on Sunday? Library, room IC2. And your homework will be due on Tuesday, October 27th. And read over the research paper assignment, and if you already know what topic you'd like, then just go ahead and let me know. Have a nice weekend. I'll see you later.